All right, so class, let's talk a little bit about power factor correction. So you may be wondering what exactly is it, but it's pretty straightforward. Um, so oftentimes power utilities or commercial customers or industrial customers are interested in improving their power factor, and how they improve the power factor are with devices called cap banks. So cap banks are just simply large, very large capacitors that are used to supply reactive power to the system in efforts to improve the power factor. So right here we have a cap bank that's probably would go into maybe like a commercial or industrial uh, customer. You know, maybe that customer has a lot of inductive loads or inductive motors, and sometimes they will use a device like this. They will hook it up to their main distribution panel in order to supply the reactive power to compensate for the inductive loading. And the same is similar to this right here. This is for a utility company. This is a pole mounted cap bank, and it does the same thing. Sometimes these things are on they have sensors where if it senses the power factor dropping below a certain amount, it will turn this cap bank on and start to supply reactive power to the system in order to improve the power factor. Or sometimes these are fixed cap banks where it just supplies reactive power regardless. All right, so when a system is operating under a bad power factor, it's undesirable to the utility company, but because it increases the system losses through the transmission and distribution power lines. These system losses mostly come from the transmission and distribution lines through the I squared R effect. So if you look at this equation right here, so this is P, right? P equals I squared R. And so this is the power that is lost through transmission and distribution lines. So whenever if you measure the resistance of a conductor, it has some type of resistance. That resistance is going to be constant. It's not going to be varying for the most part. But the thing that will be changing will be the current, because depending on the load that's uh that's connected to the system, the current will be either going up or going down. Or so whenever you have a poor power factor, more current will be flowing through your conductors, therefore increasing the amount of power that is lost through your conductors. So also a poor power factor increases the apparent power that the power utility has to supply to the system to meet the load demand. So therefore, the more apparent power supplied or needed to be supplied equals more money that the power company has to invest in energy, such as depending on what type of generation plant you're talking about, whatever energy source that generating plant is using, they have to use more energy to generate the same amount of power to do the work because of the poor power factor. So when a commercial customer is operating under a poor power factor, it's undesirable to the commercial customer as well, because the increase in current will result in larger conductors um, that have a larger ampacity. So just like I said before, when you have a poor power factor, the more current has to flow through your conductor. And so therefore you may have to use a larger conductor because due to the ampacity or the amount of current that can flow through that's rated to flow through that conductor. And so whenever you have larger conductors, of course you're gonna have to spend more money. And so, and then also, lastly, companies are interested in improving the power factor because the utility company will penalize them if their power factor is poor. So just like utility companies are not interested in supplying power that has a poor power factor because they have to spend more money on their end to supply that power. Well, if you're the one that's causing the system to have a poor power factor, well, they're going to penalize you. Or they may penalize you. So that's why some industrial commercial customers are interested in improving their power factor. So let's take a look at this next example. So the example wants you to calculate the apparent power being supplied by the source. So one way you can do it is you can calculate the total impedance. Right now, it's just the load right here. This is a 50 ohm resistor and a 30 ohm inductor. All right, so if we calculate the total current, you get V over the load, and which equals 2.06 amps at an angle of negative 30.96. So if you just kind of do a spot check to see whether or not you did it right, well, this is an inductive load. So we're expecting the current to do what? We're expecting the current to lag the voltage. So right now the voltage is at 0 degrees, and the current that we calculate is at negative 30. So this is doing exactly what we expect it to do. All right, so calculate the apparent power. Remember, the apparent power is the magnitude of the complex power. So all we need is the magnitude of the voltage, magnitude of the current, multiply together, and we get 247.2 volts amps. All right, so part two of this example. So let's place a capacitor in parallel with the load and calculate the apparent power being supplied. So whenever we do that, we put this load in parallel with this capacitor's reactance. And so therefore the current has been reduced to 1.86 amps at an angle of negative 18.16. And we calculate the complex, the parent power has also been reduced to 223.2 volts amps. So if you look at both the current and the apparent power in part two compared to part one, you can see that by placing a capacitor in parallel with your load will help improve your power losses. It will help reduce the amount of current the system has to supply, and also help reduce the apparent power. All right, so this is an extension of example one. So I want you to calculate the complex power now and the power factor of example part one and part two. So part one, we're going to use our complex power equation, S equals V times I conjugate. And so therefore we get 247.2 at an angle of 30.96 volts amps. And so we want to calculate the power factor. We can do it a couple different ways. We can use take the cosine of the voltage phase angle minus the current phase angle. And so therefore you get 0.86 lagging, or you could take the cosine of the impedance phase angle, which you get the same thing. In addition to this, as we learned in the first video, we can say power factor also equals P divided by your apparent power. And so in order to calculate your P, one way you do it is just convert this to rectangular. So you can convert this complex power to rectangular form, and so therefore you can get the actual power and the reactive power separately. And so you can use this formula right here to calculate the power factor. P over the divided by the apparent power. So therefore we get our P from up here divided by the apparent power, which is the magnitude of the complex power. And you get the same thing. Likewise, one other formula you could have used the cosine of the complex power angle, which is right here, which happens to be the same angle as the impedance. And you get the same thing. All right, so part two, we use the complex power formula, V S equals V times I conjugate. And so therefore we get 223.2 at an angle of 18.16 volts amps. Represented in rectangular form, we get 212.08 watts plus 69.56 VARs. All right. So we just perform the same method as before to find the power factor. And as you can see, the power factor went from 0.86 to 0.95 lagging. And so let's take a look at this reactive power right here. Before we had 127.17. Now it's been reduced to 69.56 VARs, which is the result of power factor correction. So let's apply this theory to another example. So in this example, it says a single phase source delivers 100 kilowatts to a load operating at a power factor of 0.8 lagging. So you calculate the reactive power to be delivered by the capacitor connected in parallel with the load in order to raise the source power factor to 0.95 lagging. So we want to raise it from 0.8 to 0.95. So we start off by writing what we know. So we know that the source is delivering 100 kilowatts. All right, so P equals 100 kilowatts. And so let's find the angle that we're going to be using our powertrain to help us solve for this, or help us visualize and solve for it. So we want to see, we want to know that what angle is this supposed to be. So it's, you take the arc cosine of the power factor before power factor correction, which is 36.87 degrees. And so so we got P equals 100 kilowatts. I wrote it right here. This is before, my power factor before, and the angle is 36.87. So we're going to solve for the other quantities values, the apparent power and the reactive power over here. So from the power triangle, we can solve for the reactive power before the power factor correction. And if you go back to the notes or the video right before this one, you can find one of those equations to help you solve for the reactive power. And so remember, in a power triangle, if you know at least two of the four variables of a power triangle, you will be able to figure out to calculate the rest of the values of that power triangle. All right, so Q before is equal to P times the tangent theta of the phase angle before. So we got 100 kilowatts times the tangent of 36.87 degrees, which is 75 kilovars. So we're going to write 75 kilovars right here. And we can use our Pythagorean theorem to solve for the apparent power, which is take the square root of P squared plus Q before squared, which is 125. Or you could have just plugged this into your calculator and just let your calculator do the work. That's fine too. So this is what the system looked like before. Let's figure out what the system is supposed to look like, what we desire it to look like. So after the power factor correction, we want the power factor to be 0.95 lagging. So let's take the same approach, figure out the angle afterwards, which is 18.19 degrees, and the reactor power, how much we want to have on the system after the power factor correction. And so what we're saying here is after the power factor has been corrected, there should be no more than 32.87 kilovars in the system or in that network. And so therefore we can calculate the parent power, which is 105.3 kilovolts amps. And so this is what the power triangle is supposed to look like afterwards, or the system is supposed to look like afterwards. Notice how the power remains the same because we need that power in order to do our work. We don't want to adjust this power. So this power is going to stay constant. But what needs to change is this reactive power right here. In this case before, we have too much. So we want to reduce it to no more than this right here. So in order to figure out how much reactive power your capacitor needs to supply is you just simply take the difference. In this case, you take your reactive power before, which is 75, and you subtract it from your reactive power afterwards, 32.87 kilovars. And so you find that difference, and that's how much reactive power that capacitor needs to supply to the system in order to compensate the inductive load to increase the power factor to 0.95 lagging. All right, so let's go a little step farther. So let's say if the system is operating at a frequency of 1 kilohertz and the source voltage is 12.47 kilovolts, what size cap bank will need to be installed? And we're going to assume uh, and This is what we're going to assume. Assume the voltage source, which is in a system. In a system, typically the things are installed in parallel. But for this particular example, we're going to assume that the voltage source is in parallel with the cap bank, which is a fair assumption. All right, so we can start off by using this formula right here. This is the formula that we derived in the last video. Z equals the magnitude of the voltage squared divided by the complex power. And so this is coming from our derivation of the complex power to solve for the impedance. And so since we know that this impedance is going to be capacitive, so therefore, so remember the impedance, if you express impedance as Z, you're saying that you have a combination of real and imaginary. But impedance can also equal just only uh, like a real number or imaginary number, or an impedance can also equal just only a resistance value, or it can also equal just only a reactive value. So in this case right here, we're trying to calculate the impedance of a capacitive load. So we know if it's just only a capacitive load, it doesn't have any resistance in that load. So therefore, we can reduce or substitute the the reactive element, the capacitive reactance, with the impedance, like I've done right here, and also the complex power. We know we're not going to have any real power. All the power is going to be reactive, so we can substitute the um the complex power to just only a reactive power. So that's kind of how this derivation works. So we just plug and chug, we'll get a capacitive reactance of 3.69 kilo ohms. And if we do some reverse engineering, we can solve for the actual capacitive value, which is 43.19 picofarads. So 43.19 picofarads will have to be installed on that network, or that system in parallel, in order to improve the power factor to 0.95 lagging. All right, so consider this example or this analogy to kind of help bring home the understanding of what power factor correction is all about. Let's say let's say that it costs you $20 to go in fuel, to go to work and come back home. $20. So every time you need to go to work and come back home is $20. $20. $20. All right. So you make a friend and you say, "Hey, you can come stay with me and at my house, and we work at the same place, so you can just ride with me." Well, what does that friend do? That friend adds extra weight to your vehicle. So now the vehicle is not only trying to take support the weight of you, it's also trying to support the weight of your friend as well. And so now, next time you fill up, you're like, man, it costs me twice as much to go to work and come back home. So that's kind of what a poor power factor is doing to the system. It's is making the um the generating plant or the generating utility spend extra money and fuel to do the same work. In this example right here, the work that's being done is you're going from home to work, from work to back home. That's all you're getting out of the deal is you're going is the ability to go from home to work and from work back to home. But now since you added your friend, and now you're taking your friend as well, so that friend symbolizes the inductive loads. And so now you're having to spend more energy, more fuel to take you and your friend to from home to work, from work to back home. And so that's kind of a real life example of power factor, how power factor works. All right, so if we apply this to a real life example, so this is something similar to what a utility company will be doing. It'll be power, supplying power at a poor power factor, so therefore it has to spend more money in fuel to supply that power. More current is being transmitted through the distribution and transmission lines. So therefore, you're losing more power through your transmission line through the I square R effect. So in terms, what the utility company can do is install a cap bank that's in parallel with the system, and so therefore that cap bank is doing is compensating the inductive load that's being seen by the system. So therefore, that inductive load, not all of it, will be seen by the the utility plant or the generating plant, which reduces the current that flows through the system, flows through the transmission line, reduces power losses, and overall increases the power factor. So I hope this video was helpful. If you have any questions, feel free to reach out to me. This is somewhat of this is a new concept, so it may take a few times to watch this video, rewatch it, look up some other sources or videos online. YouTube is a great resource. Just type in power factor correction in YouTube. You can find all kinds of videos on YouTube. Google, I mean, there's all kinds of things out there that addresses this topic. But if you have any questions and you want to reach out to me, feel free to let me know.